Close your eyes. 20 years from now, a tiny probe the size of a smartphone tears through the darkness between stars. It carries no crew, no fuel tank, no bell-shaped engine, only a wafer of electronics glued to a gossamer sail. It has crossed 4 light years in a single human generation. And its journey began here, on Earth, pushed not by fire, but by light. That is the audacious promise behind engines to Alpha Centauri, the nearest stellar system to our Sun, at about 4.37 light-years away. To arrive there in roughly 20 years, anything we launch must cruise near 1/5 the speed of light, around 60,000 kilometers every second. At that velocity, a speck of dust hits like a bullet, and a small pointing error becomes a miss measured in millions of kilometers. Yet a handful of radical ideas suggest the trip could be possible within our lifetime. First, let's feel the scale. Our swiftest machines, Voyager, New Horizons, and Parker Solar Probe, are marvels of human engineering. Parker briefly exceeds 150 kilometers per second by diving deep into the Sun's gravity well. Astonishing? Yes, but compared to the 1/5 light speed we need for a 20-year Centauri sprint, it is still hundreds of times too slow. Rockets that carry their own propellant run into cruel math. Every kilogram of fuel you add is a kilogram you must also accelerate. That is the tyranny of the rocket equation. So the first radical move is simple to say and hard to do. Leave the propellant at home. Enter the laser sail. Picture a mirror-bright sheet, meters across and thinner than a human hair, with a postage-stamped spacecraft camera, sensors, star tracker, and radio mounted beneath. On Earth, a vast phased array of lasers, synchronized so their wave crests add up like a choir, pours tens to hundreds of gigawatts of light onto that sail for only a few minutes. Photons have no rest mass, but they carry momentum. When they bounce off the sail, they push. With enough power, that push becomes a continuous shove, and the craft leaps to extraordinary speed without carrying a drop of onboard propellant. This is the essence of laser-pushed flybys, such as the breakthrough Starshot concept. It sounds like science fiction until you notice how many ingredients already exist. Ultralight reflective films are real. Microcameras and chip-scale radios are real. Phased laser arrays and adaptive optics are real. The Stretch is doing all of it at once, at unprecedented scale, and surviving the ascent. A sail must stay stable under brutal acceleration tens of thousands of G for minutes. It must not wrinkle, tear, or overheat. The beam must be aimed through a churning atmosphere or from space without wandering. And the tiny probe must ride that beam like a surfer holding steady on a glass-thin board. What do we gain if we pull it off? A swarm. Dozens or hundreds of gram-scale probes could streak outward, one launched every week. Most would fail, some would survive. Roughly 20 years later, the survivors would blitz through the Alpha Centauri system at blistering speed, snapping images, tasting the stellar wind, sampling dust, and beaming their data toward Earth. 4 years after that, because light itself needs 4.37 years to cross the Gulf, the first postcards would arrive. Picture opening your feed in the 2052nd and seeing the first true color close-ups of another sun-like star and its environment, sent by a spacecraft lighter than a chocolate bar. Laser sails are not the only engine on the table. Another path keeps the power source with the ship, but seeks better mileage than chemical fire. Nuclear thermal and nuclear electric propulsion are the serious, near-term options. Nuclear thermal rockets work like supremely hot kettles. A fission reactor superheats hydrogen and throws it out a nozzle. They are 2 to 3 times more efficient than the best chemical rockets and could shorten trips across the solar system. Nuclear electric propulsion uses a reactor or radioisotope power to run ion thrusters, sipping propellant at incredible efficiency. These systems will transform deep space missions. But for a 20-year dash to Alpha Centauri, they are not enough. Today's nuclear and ion technologies can shave weeks to Mars, months to Jupiter, and years to Pluto. They will not reach 20% of light speed. To leap that far, you either push from the outside as lasers do, or you carry a star in your pocket. Fusion drives are the pocket star idea. Concepts range from pulsed fusion detonating tiny fuel pellets, so each microblast adds momentum to magnetic nozzles that channel a continuous fusion plasma. If humanity ever masters compact fusion power and the magnetic plumbing to turn it into directed exhaust, it could change everything. But the engineering mountain is enormous. You must confine plasma hotter than the sun, convert that energy into thrust without melting your engine, and reject a river of waste heat into the blackness of space. All of it must fit into a spacecraft that is light, reliable, and serviceable by no one for decades. Then there are antimatter dreams. Antimatter is the ultimate fuel. When it meets normal matter, nearly all the mass becomes pure energy. A few milligrams could, on paper, deliver the punch of tons of chemical propellant. For now, though, it remains a dream. We can make only specks of antimatter in laboratories, at costs that make gold look cheap. Storing it safely requires magnetic bottles that can never fail, because touching any wall would trigger an explosion. And even if you had enough, shaping that annihilation into clean, directed thrust is a challenge that lives far beyond our current playbook. None of these obstacles are small. Interstellar space is not empty. Dust grains at relativistic speeds can sandblast a spacecraft. A forward shield might need to be a sacrificial bumper, or even a spray of vapor released ahead to absorb hits. The thin gas between stars creates a drag you must budget for. Electronics have to endure decades of radiation and cold without repair. Autonomy is mandatory. After coasting for 20 years, the probe must point its camera, catch a flyby window measured in minutes, and fire its data home with exquisite timing. Communication is its own beast. A gram-scale probe cannot carry a large transmitter, so the link budget is brutal. One clever solution is to use the sail itself as an antenna or mirror, turning the reflector that pushed the craft into the dish that sends its voice back. Another is to build giant receivers on Earth, or the moon radio arrays or optical telescopes to listen for whispers from the dark. Either way, the earliest images would trickle in years after the flyby, a delayed sunrise for anyone watching at home. So why talk seriously about a 20-year trip to Alpha Centauri? Because, for the first time, we can sketch a credible end-to-end system that might do it. Not with a luxury starship and a miracle drive, with chips and sails, beams, and swarms. With a plan that uses Earth as the engine and the cosmos as the racetrack. Build the beam infrastructure once, and it could also nudge satellites into safer orbits, power cargo to the moon, and demonstrate beamed energy flight closer to home. Every step would be valuable, even if the stars remain a hard target. Here is how this story will unfold. In the next chapters, we will define the destination and the speed budget. We will unpack laser sail physics, beam arrays, sail materials, thermal limits, and beam riding control. We will tour nuclear thermal and nuclear electric propulsion, what they can do now and what they could do soon. We will peek at fusion and antimatter without hype, mark what must change for them to leave the lab, and stay honest about engineering risk, cost, and the global cooperation such a project would demand. For now, hold one image in your mind: a night sky, a bright point that is not quite a star, only a glint on a sail, riding a beam we made, racing toward another Sunday. Alpha Centauri is about 4.37 light-years away. A credible first mission pushes for minutes, coasts roughly 22 years, near 1/5 the speed of light, flashes past in minutes, then waits 4.37 years for the signal to arrive. If the probe transmits at closest approach, launch to first image is about 26 years. Speed sets everything. At 0.2 c, about 60,000 kilometers per second, the cruise takes 21.9 years. At 0.1 c, it doubles. At 0.3 C, power, heating, pointing, and dust hazards jump. Around 0.2 C is the slim lane where bold meets barely feasible. The spacecraft is gram scale. The sail spans a few meters, mirror bright, and patterned so it recenters itself under a beam like a shuttlecock in airflow. The engine sits on Earth, a phased array of many modest lasers whose wave fronts lock into one steerable column. For a few minutes, the array pours tens to hundreds of gigawatts onto the sail. Photons bounce, momentum transfers, and the craft leaps without propellant. The push is savage but short. 2 minutes to 0.2 C means an average acceleration near 500,000 meters per second squared, about 50,000 G. Even 10 minutes is near 10,000 G. Humans cannot ride that, but a chip can if every trace, bond, and lens is built for shock. Heating is the other killer. The sail must reflect almost all the incoming light at the beam's color and radiate waste heat in the infrared. It should climb warm, not melting. Stability is as hard as strength. Any drift must create a restoring torque that nudges the sail back to the beam's core without moving parts. Think of balancing a broom by sliding your hand. Here, the optics do the sliding. Tiny actuators, cold gas puffs, atom-scale mass drivers, or electrostatic tabs trim attitude during the push and later in cruise. Beaming through air adds a fight. Turbulence warps light like heat over asphalt. Adaptive optics, proven on large telescopes, pre-distort the outgoing wave so it arrives flat after the atmosphere. High, dry sites help. Some designs move the array to orbit or a lunar plane, removing, seeing, and widening the horizon at the cost of assembly in space. Pointing tolerances are brutal. A tiny aim error today becomes a huge miss 20 years later. Calibration starts before launch, continues during the push, using feedback from the sail's glint, and then relies on the probe's star tracker to hold attitude to arcseconds. Most of the correction must happen up front. Power is the elephant. Delivering on the order of 100 gigawatts for minutes is outrageous but pulsed. You don't build one city-sized laser. You tile thousands of efficient emitters, so they add coherently. Energy is banked and then dumped into the array. The price is steep, but the facility is reusable, capable of debris clearing, satellite nudges, or cargo sails to the moon between interstellar shots. The sail is a materials frontier. Metals are shiny but heavy and often absorb too much. Dielectric films and photonic crystal membranes can reflect strongly at the beam's color while shedding heat in the infrared. Thicknesses are in the hundreds of nanometers. Geometry matters: conical, spherical, cap, or a flat disk with graded reflectivity, so it rides true. Space is not empty. At 0.2 C, dust motes hit with rifle-like energy. A tiny forward shield stacked layers of tough, low-Z material can vaporize grains before they reach the payload. Some concepts release a faint gas cloud ahead of the probe to ionize impacts. Radiation flips bits. Hardened electronics plus error. Correcting codes keep memory honest. The rare big particle is the wild card. A swarm spreads risk. Communications are tight. A gram-scale probe cannot host a large dish. One trick is to repurpose the sail as a high-gain mirror for a tiny laser transmitter. Another is to aim at a prepared receiver, a giant telescope on Earth or on the Moon, built to listen for whispers. You budget bits, send thumbnails first, then trickle detail over months. A handful of great images may be the entire treasure. Why a flyby and not orbit? There is no mass or energy to break at Alpha Centauri unless a second beamer waits there. A flyby is still rich. The system includes Proxima Centauri, likely with a temperate rocky world, and the Sun-like pair Alpha Centauri A and B. Even at high speed, you can sample stellar winds, dust, magnetic fields, and the color of reflected planetary light. A launch cadence dozens or hundreds over years hedges, failures, and targets different paths through the system. What about a bigger, slower craft with a nuclear engine? That road is excellent for the solar system. Nuclear thermal and nuclear electric propulsion move heavy payloads far and fast by inter-planet standards. For a 20-year interstellar sprint, the practical energy per kilogram falls far short of zero. 2C. Unless compact fusion or something even more radical arrives flight-ready, beamed sails are the only lane that reaches this timescale with components we can plausibly build. That is the speed budget, the pointing budget, and the patience budget in one picture. You front-load almost everything on Earth. You accept a fierce, brief push, a long, quiet coast, and a whisper returning years later. In exchange, you get the first credible shot at interstellar exploration within one generation. Next, we'll open the beamer and walk through its anatomy, the phasing, the optics, the sights, and the control loops that turn ground or regolith into an engine for another sun. Open the beamer. Imagine a flat field of laser tiles stretching for kilometers, each no bigger than a pizza box. Alone, a tile is modest. In chorus, thousands behave like one coherent instrument, a phased array that sculpts a beam, steers it without gimbals, and drives a sail only grams in mass. A phased array is less like a lighthouse and more like a stadium doing the wave. Every emitter times its flicker, so peaks and troughs add in a chosen direction. Where phases match, light piles up. Where they do not, it cancels. The result is a column of photons, pencil, thin at the start, that holds together far longer than any single laser could. Synchronization is the hard part. Millions of tiles must agree to within fractions of a wavelength. It sounds brutal, but it lives in the same family as phased radar, 5G antenna farms, and adaptive optics we already run on Earth, just scaled up and tuned for raw power. The first adversary is air. Look across hot asphalt, and you see shimmering. The same turbulence bends a laser. Adaptive optics fixes that in real time. A wavefront sensor measures how the atmosphere twisted the light, and deformable mirrors or electro-optic tiles built into the array predistort the outgoing beam, so it arrives flat. Large observatories already do this with artificial guide stars. Our beamer can use the sail's own glint as a guide. Cameras near the array watch that pinprick and feed corrections thousands of times per second, keeping the beam tight while the sail is still close to Earth. Diffraction sets the second limit. Any finite aperture makes a beam that spreads. The larger the array, the tighter the spot stays with distance. With a kilometer-class array operating in near-infrared, the spot remains compact over thousands of kilometers. That defines the push zone. The plan is simple. Accelerate hard while the sail is still near Earth for only a few minutes, then shut off and let the probe coast for decades. Pointing is unforgiving. A microradian aim error, 1 part in a million, turns into hundreds of kilometers of miss years later. So we stack control loops. Coarse pointing aims the array at the departure corridor. Adaptive optics fights the air. Fine phasing sharpens the main lobe. The sail itself is shaped to self-center, like a badminton shuttle that drifts back into the airflow. Microactuators, electrostatic tabs, piezo strips, or tiny moving masses trim attitude during the push and later in cruise. Power is the elephant in the hangar. We need tens to hundreds of gigawatts, but only for minutes. That points to a facility that charges slowly and discharges fast. Grid power fills massive storage-pumped hydro, flywheels, molten salt heat, or big batteries over hours. On a clear window, the array fires and empties that bank in a burst. High-efficiency lasers and power electronics matter because every percent lost becomes waste heat. On Earth, cooling towers and heat exchangers dump it. In space or on the moon, heat leaves through radiator wings, big dark panels that glow faintly in the infrared. Site selection shapes everything. High, dry deserts like the Atacama or the Antarctic Plateau offer thin, steady air. Multiple ground sites can share a schedule or back each other up against weather. Space-based arrays dodge the atmosphere entirely, but demand assembling and aligning thousands of tiles in orbit, powering them with large solar farms and cooling them with radiators. The moon is attractive. No air, stable ground, and long lunar nights that help cooling. The price is power storage, dust control, and the logistics of building anything large off-world. Safety and governance are essential. A beam bright enough to push a sail must never hit aircraft, satellites, or the wrong patch of ground. The array would integrate sky mapping radar, satellite ephemerides, and shutter interlocks. If anything crosses the corridor, the beam shuts down in milliseconds. International oversight, licensing, and transparent operations are mandatory from site choice to launch windows to post-shot logs, because this is not just a machine, it is a global asset. Now the sail. The best mirror is not metal foil, but a photonic fabric. Ultra-thin dielectric layers tuned to reflect almost all of the beamer's color while radiating heat in the infrared. A real density is in grams per square meter. Geometry is biased, so the sail naturally recenters under the beam. Some designs spin the disc for stiffness, like a coin that stays flatter while spinning. Others use a shallow cone or curved profile to generate a restoring torque that resists drift. Thermal paths are as important as strength. The sail must throw off a trickle of absorbed heat continuously, or it will wrinkle, tear, or fuse. The payload hides in the sail's shadow to reduce heating. It is a wafer with a camera, spectrometer, star tracker, processors, and a tiny laser for the return link. The rim can carry microthrusters for trim after beam out. During the push, the sail's optics do most of the steering. After the push, sunlight pressure and tiny impulses keep attitude steady for years while the probe crosses interstellar space. What does a firing sequence feel like? Hours before launch, the array phases against a calibration target and confirms clear skies. The sail unfolds from a small kick stage to a safe distance. The array acquires the glint, locks the wavefront, and ramps power. For 3 to 10 minutes, the craft rides a column of light, acceleration fierce, but smooth. As it recedes, the spot broadens. When flux falls below useful levels, the beam shuts off. The sail curls slightly and turns edge, on to minimize dust impacts, then settles into a decades-long cruise. Reusability turns the beamer from a stunt into infrastructure. Between interstellar shots, the array can fly smaller sails to cislunar space, clear debris by nudging dead satellites into controlled decay, and beam power to tugs moving cargo to the moon. Those near-term services create a market that pays for upkeep while the interstellar program matures. Cost and risk are managed by modularity. Tiles, lasers, drivers, phase modulators, and cooling are mass-produced like solar panels. If 1% fail, the beam barely notices. Technicians swap dead modules on a schedule. Sail materials are iterated in parallel metasurfaces, nanolaminates, diffractive films, and flight tested until one proves strong, reflective, and cool enough to graduate. This is the anatomy of an Earth-powered engine for the stars. Phased light, adaptive optics, hard limits from diffraction and heat, fast charge and faster discharge, strict safety, and a sail that is more lens than cloth. Audacious, yes, but every piece builds on tools we already use. Next, we put the sail under stress beam tests, thermal tests, and accelerations high enough to turn a pebble into powder and see what breaks first. Start with heat, because heat ends most experiments. A laser sail survives only if it reflects almost everything at the beamer's color and dumps the tiny remainder as infrared glow to deep space. In the lab, that means measuring 3 numbers with painful honesty: reflectivity, absorptivity, and emissivity. Engineers stretch a square of the candidate membrane across a light frame, place it in a vacuum chamber, and drive it with a tunable near-infrared laser while thermal cameras watch. Even 1% absorption at gigawatt-level flux would cook a membrane in seconds, so the stack is tuned like a musical instrument. Dielectric layers, a few hundred nanometers thick, bounce the chosen wavelength. while the back surface radiates strongly in the mid-infrared. Researchers map hotspots, then tweak thickness and doping until the film runs warm but not wild. Next comes stress. The beamer's push is not gentle. Tens of thousands of G for minutes is a mechanical trial few structures have seen. Classic pull-to-break tests do not capture it. Teams combine pulsed optical loading that ramps over milliseconds, shock tables that yank the frame with controlled jerk, and compact centrifuges that spin tiny coupons at extreme G for seconds. Strain gauges etched into the film report how ripples form, how edges curl, and when the first microtear appears. A small, deliberate spin often saves the day. Like a coin that stays flatter while it spins, the rotating membrane stiffens and damps wrinkles before they grow. Beam riding is a control problem disguised as a material problem. A perfect mirror still drifts if pressure is not symmetric. The sail must act like a shuttlecock, generating a restoring torque whenever the spot slides off-center. Designers test this in beam tunnels, long vacuum tubes, where a coin-sized sail rides a kilowatt beam, while high-speed cameras track attitude. With the right profile and a tiny spin, the sail recenters itself without electronics, leaving only fine trim for rim actuators that flex by microns to nudge the torque. The goal is passive stability first, active stability second. Thermal runaway is the silent killer. A small temperature rise can change optical constants, boost absorption, and feed the fire. To break that loop, the top stack reflects narrowly around the beamer's color, while the backside is almost black in the thermal band. Microscopic heat paths carry hot spots toward the rim, which radiates like a cold stove element. In tests, engineers deliberately detune the beam by a hair and watch whether the sail recovers or blisters. A pass means the film self-heals thermally. A fail means a redesign. Dust and pitting matter before the first interstellar grain ever hits. To simulate years of wear in a day, labs blast samples with ion beams and fine dust at high speed, then remeasure optics. A good sail tolerates freckles. A great sail keeps riding because its control law treats small holes as noise, not catastrophe. Deployment is a trap of its own. The film must unfold from a package the size of a thermos without creasing into scars. Gravity lies on Earth, so teams use parabolic flights, drop towers, and thermal vacuum chambers with near-invisible tethers. A gentle spin tensions the membrane like a drum, or a shape memory ring pops it to a clean circle. Every hinge, crease, and seam is rehearsed until deployment looks boring on camera. Now point a real beam. Subscale flights in low Earth orbit are the crucible. A CubeSat releases a handkerchief-sized sail. From the ground, a modest phased array paints it with tens of kilowatts for seconds, enough to test wavefront sensing, adaptive optics, and self-centering. Onboard cameras watch for ripple modes, while telemetry shows how often the beam corrected for high-altitude turbulence. The electronics ride in the sail's shadow but still feel the jerk. To survive, the payload goes flat. Imagers bonded to the substrate, planar antennas printed into the wafer, and a laser transmitter on a tiny heat spreader. Power comes from thin-film photovoltaics and a tiny buffer battery. Boards are shaken, baked, frozen, and shocked. Shielding earns its own trials. At 1/5 light speed, a dust grain is a bullet. A layered, low atomic number bumper polyimide, aerogel, or graphite foam sits ahead of the payload. Impact guns accelerate micron-scale particles into coupons to verify that the first layer vaporizes the grain and the second soaks the plume. The shield must survive not one hit, but thousands. Each gram in front buys a measured reduction in expected damage. Navigation is tested the quiet way. After the push, the sail turns edge-on and coasts, guided by starlight. Star trackers the size of a postage stamp confirm attitude to arcseconds, while field emission or electrospray microthrusters deliver nanonewton nudges. Labs measure thrust on torsion pendulums, then bake the units, freeze them, and retest until the numbers repeat. Finally, practice failure. Shutoffs must be automatic if the glint winks out or if the beam wanders outside the safe corridor. The sail should have a reflex, tip a few degrees, shed the light, and live to try again. If a tear starts, the pattern routes stress around it. If the array jitters, the control law forgives. Teams script ugly nights on purpose, hotter beams, dirtier air, delayed phasing, and call a design mature only when boredom, not adrenaline, defines the logbook. This is how you break a dream until it stops breaking. When a film rides hot without burning, when a beam shoves hard without flipping, and when a wafer survives the punch with its mind intact, you have a sail that can meet the beamer outside and not flinch. With materials and control in hand, we can widen the lens and ask what else might cross the void. Nuclear thermal and nuclear electric engines that trade sprint for stamina within the solar system, and fusion concepts that try to carry a star in the pocket of a ship. Those are the next contenders on the bench. Set the sail aside for a moment and roll a different kind of engine onto the floor, one with a core that cracks atoms. Nuclear thermal propulsion looks almost old-fashioned compared to laser beams, but it is the most mature leap beyond chemistry that we can build with today's toolkit. Picture a compact fission reactor sitting behind a tank of liquid hydrogen. The reactor doesn't make electricity. It makes heat, ferocious, steady heat. Hydrogen is pumped through the reactor's fuel elements, expands into a white-hot gas, and roars through a nozzle. Because hydrogen is the lightest molecule, it leaves fast. And fast exhaust means efficient thrust, where the best chemical rockets manage specific impulse around 400 or 500 seconds. Nuclear thermal aims near 900. That's like doubling the miles per gallon without shrinking the engine. What does that buy you? Shorter trips and heavier payloads across the solar system. A nuclear thermal stage can cut a crewed Mars journey by months, widen launch windows, and carry more shielding, water, and science gear. It delivers real, high thrust enough to leave Earth orbit briskly, to break into Mars orbit, to rendezvous with cargo. Ground tests in the late 20th century proved reactors could run at these temperatures for hours. The modern twist is materials. Fuel elements that survive cycling without cracking, coatings that keep hot hydrogen from chewing the reactor to pieces, and turbomachinery that lives in a bath of cryogenic propellant on one side and furnace heat on the other. Safety doctrine is straightforward. You test everything to death. You keep the reactor cold and subcritical during ascent, and you only go nuclear hot once you are safely in space. Nuclear electric propulsion swaps heat for thrust for heat to electricity to thrust. A reactor drives a generator, and that power feeds ion engines or Hall thrusters. The exhaust is a whisper, not a roar, but the efficiency is astonishing. Instead of hurling propellant out at a few kilometers per second, ion engines flick it away at tens of kilometers per second or more. The catch is patience. Thrust is measured in millinewtons to newtons, so you accelerate for months and years rather than minutes. Solar electric missions have already shown the path by using kilowatts of sunlight near Earth. A nuclear plant lets you keep that power far from the sun where solar panels fade. With nuclear electric, the hidden dragon is heat rejection. Every watt that doesn't leave as thrust must leave as waste heat through radiators. And radiators are area and mass. A megawatt-class ship needs football field-sized panels glowing gently in the infrared. The engineering is manageable think-pumped loops, heat pipes, and deployable structures, but it sets the scale. You also budget radiation shielding, not for people in our tiny probe, but for electronics that must survive for decades. The advantage is exquisite control. Electric thrusters throttle smoothly, point precisely, and can run for years without a rebuild. For heavy robotic cargo trains, outer planet flagships, and deep space tugs, nuclear electric is quietly transformative. So why don't these engines carry us to Alpha Centauri in 20 years? Energy makes the case in one line. To push 1 kilogram to 1/5 the speed of light, you must pour roughly a quadrillion and change joules into it thousands of times more energy per kilogram than chemical propellants can deliver, and still far above what practical fission systems can push through a rocket nozzle when you include the massive tanks, radiators, and structure. Nuclear thermal is wonderful at grabbing big chunks of delta V inside a planetary system. Nuclear electric is wonderful at sipping propellant to sculpt orbits for as long as your patience and power last. Neither comes within shouting distance of 60,000 kilometers per second with a self-contained stage you can launch in one piece. There are hybrid dreams, of course. You could imagine an Earth-to-deep space architecture where nuclear thermal stages lift heavy infrastructure, the pieces of a laser array, lunar power farms, or logistics depots quickly around the inner solar system. Nuclear electric tugs could then ferry those pieces to high orbits or to the moon with excellent efficiency, assembling the beamer that ultimately pushes gram-scale sails to interstellar speed. In that picture, fission engines don't race to Alpha Centauri, they build the racetrack. Even within the nuclear family, choices ripple everywhere. Nuclear thermal uses hydrogen because performance scales with light propellant. That demands good cryogenics and insulation, venting boil-off safely, and refilling tanks in orbit. Nuclear electric likes noble gases such as xenon or krypton, which store conveniently and behave well inside thrusters. But global supply and cost become real program issues if you start talking about dozens of multi-ton missions. Then there's maintenance. An interstellar flyby probe can be tiny and disposable. A nuclear tug is an asset you operate for years, so you design in modular reactor cores, replaceable power converters, and thrusters you can swap. Public perception matters too. A fission reactor heading to orbit concentrates attention. The response is openness. You use flight-proven containment. You publish safety analyses. You choose ascent trajectories with the same care commercial crew vehicles get. And you place the Go Hot command only where an abort can't rain debris on anyone's farm. Nuclear electric can feel less dramatic, but in both cases the governance is the same. International transparency, launch, window discipline, and telemetry that proves you fly the way you promised. What about performance numbers people can hold? Think of nuclear thermal as the sprinter of the pair, useful for big, decisive burns and time savings counted in months. Think of nuclear electric as the marathoner's small steps, always on, carving impossible-looking changes if you give it a year. A flagship science craft riding multi-hundred-kilowatt electric propulsion could tour multiple moons of a giant planet, hop orbits, and carry instruments without starving the bus. A cargo hauler could push thousands of kilograms to lunar orbit routinely, seeding the factories that make sails, mirrors, and beam tiles by the crate. All of this says something important about the path to the stars. The fast concept, a laser sail, is light, brittle, and specialized. The steady concepts, nuclear thermal and nuclear electric, are heavy, robust, and multi-purpose. They are the ships and tugboats of a cislunar economy. If we are serious about an interstellar test this century, we will almost certainly build and fly both kinds of engines. One pays for the other. One lays power cables, moves mass, and cuts travel times between worlds. The other fires a single brilliant shot that sends a postcard to another sun. Stated plainly, nuclear thermal and nuclear electric will not win the 20-year race to Alpha Centauri alone, but they may be the reason the race can start. They get people and hardware to the right orbits. They make lunar industry plausible. They let us practice long-duration operations, autonomous navigation, and deep space fault management, the same disciplines a gram-scale probe needs on its lonely crossing. And they give us options if we ever choose to send something larger than a wafer, something that must break into orbit around a distant star and stay. Which brings us to the tempting middle ground between today's reactors and tomorrow's fantasy fuels. Fusion. If fission is a hot kettle and electric is a long wire extension cord, fusion is the pocket star. It promises exhaust velocities that finally make interstellar speeds sound like engineering instead of magic. Next, we will thread through pulsed pellets, magnetic bottles, and the brutal arithmetic of turning sun core temperatures into clean, directed thrust without melting the engine that holds it. Call it the pocket star. Fusion propulsion bottles, sun-level heat, lets nuclei merge, and throws that fire out the back as thrust. If chemical rockets are campfires and fission rockets are blast furnaces, fusion is a sliver of stellar core you carry. It tempts interstellar planners because exhaust velocities can be a real fraction of light speed. Faster exhaust means less propellant for the same final speed and a path, in principle, to Alpha Centauri. Two families dominate. Inertial confinement fusion lights tiny fuel pellets in rapid pulses. Magnetic confinement fusion cradles a continuous plasma inside magnetic bottles. Both force-like nuclei together, usually deuterium and tritium, which fuse at the lowest practical temperature. For rockets, both must deliver not just net energy, but controlled thrust, huge exhaust velocity, and hardware that survives its own reactor. Start with pulsed fusion. Imagine a stream of peppercorn-sized pellets, each a layered sphere of frozen fuel. Lasers or ion beams strike a pellet from all sides, crushing and heating it until a bubble of fusion pops at the core. Fire many times per second. Catch the plasma in a magnetic nozzle, a funnel made of force, and you get thrust as a drumbeat of tiny explosions. Pros: immense exhaust speed, clean, on, off control. Cons: fearsome repetition rate, brutal alignment, erosion where the hot plume meets matter, and wall plug. Efficiency: if the drivers waste power as heat, the vehicle becomes a radiator. Magnetic confinement trades bang bang for steady push. A torus or mirror of plasma is held by strong fields, heated to hundreds of millions of degrees, and allowed to leak out through a magnetic nozzle. Specific impulse could reach tens of thousands of seconds with smooth throttle. The price is mass and complexity. Big superconducting coils, cryogenics, power converters, and a nozzle that must turn swirling fire into a tight jet. Neutrons are the hidden tax. The easiest fuel, deuterium, tritium, throws most of its energy into a 14 MeV neutron that magnets cannot steer. Neutrons make heat in the wrong places and slowly damage whatever they hit. On Earth, you capture that heat in a blanket. In space, every kilogram of blanket and radiator is mass you must accelerate. A neutronic fuel's deuterium, helium-3 or proton-boron-11 spit out mostly charged particles you can steer, but they demand far higher temperatures and exquisite purity. Helium-3 is rare. P-11 burns reluctantly. You do not dodge the engineering, you shift it. Even after you pick a fuel, you face plumbing, turning fusion fire into thrust. A magnetic nozzle is a shaped set of fields that catches a hot, expanding plasma and lines it up like a marching band. Edge instabilities try to shred the flow. Any energy that misses the nozzle becomes waste heat radiators must throw away. With a fusion engine lit, those wings glow in the infrared. If everything works, a pulsed fusion rocket might fling exhaust at tens of thousands of kilometers per second. A steady magnetic rocket might push a heavy ship at millimeters or centimeters per second squared for months, quietly building interstellar class Delta V. A mission could accelerate for a decade, flip, and decelerate for a decade into the target system. That solves the flyby problem. You can brake and stay, but invites big radiators, heavy shielding, and a reactor you trust for decades. There are middle paths. Magneto-inertial fusion compresses a target inside a magnetic cage, splitting the difference between pellets and bottles. Z-pinch and plasma-focused devices create momentary fusion by ramming huge currents through a fuel column. Married to a magnetic nozzle, each burst becomes a push. Direct conversion schemes harvest the kinetic energy of charged fusion products as electricity, trimming mass, and feeding high-efficiency electric thrusters downstream. Every idea hunts the same prize: compact, efficient, well-behaved fusion you can fly. Then comes the Bussard ramjet, a workaround for carrying fuel. Fit the ship with a magnetic scoop thousands of kilometers wide, sweep up interstellar hydrogen at relativistic speed, and burn it. The catch is density. Space is so empty that scoop drag can outweigh the thrust from collected fuel at any realistic efficiency. You get a brake, not an engine, unless your scoop and reactor verge on the miraculous. Safety is no softer than the physics. A stalled core still carries activation products. A cooling failure dumps megawatts into structures that fail fast. A misbehaving plasma can spit heat onto a spot and ruin a coil in seconds. The cures are redundancy, passive safety, and ruthless testing. Multiple loops, quench protection, sacrificial liners, automatic shutdown when sensors twitch. Why keep fusion on the list? Because if it works even once, it redraws the map. It turns heavy human missions to the outer planets. It makes decelerating probes into nearby systems logically thinkable. It lets you bring a lab, a relay antenna, and a shield that shrugs off a nasty dust hit because you are not shaving grams. The beamed sail is our sprinter. Fusion is the ship with stamina. For a 20-year Alpha Centauri sprint, fusion is not the first bet. The laser-pushed wafer is smaller, cheaper, and more now, even if it only buys a flyby. Fusion is the slower bet with the huge payoff. The path forward runs through near-term winds, higher temperature superconductors for lighter magnets, radiation-tolerant alloys, compact pulse drivers that turn wall, plug power into clean, shaped bursts, and magnetic nozzles tested at the edge of stability. If a society can build one engine that bottles a star and another that rides sunlight set free by lasers, it can choose its pace to the nearest sun. We start with the arrowhead, the wafer sail that flashes by and whispers back. We aim next for the ship that can slow down and stay. Between those landmarks waits the most potent and most troublesome idea in propulsion, the one that annihilates mass into energy with theatrical perfection: antimatter. It is real. We can make it by the nanogram, and yet it resists being tamed. Next, we ask what an antimatter engine would really take, and why its problems begin long before ignition. Call it the crown jewel of rocket fuels. Antimatter doesn't burn, it vanishes into pure energy the instant it touches ordinary matter. A speck of antimatter meeting a speck of matter converts almost all of their mass into energy. E equals mc squared. That staggering energy density is why antimatter lives in every bold wish list of engines for Alpha Centauri. Then the bill arrives. We can make antimatter, yes, for real, but only in dust mode amounts and at absurd cost. And after you've made it, you face the harder part: keeping it. You can't pour antiprotons into a metal tank. They annihilate the tank. Modern tanks are electromagnetic cages that levitate the particles in ultra-high vacuum at cryogenic temperatures. If the fields blink or a seal hiccups, your precious fuel disappears in a flash of heat and radiation. In short, production is expensive, but day-to-day containment is the true job. Now pretend we solved the jar. What do we build with it? The most conservative design is a thermal antimatter rocket. Here, annihilation happens in or near a heat exchanger, and that hot hardware warms a propellant, usually hydrogen, that expands through a nozzle. Think of it as a nuclear thermal rocket where the reactor core is replaced by annihilation heating. The upside is control. You throttle by metering antiprotons. The downside is brutality. The first solid surface that sees the reaction gets battered by high-energy particles and spot heating. Performance beats chemical rockets and can rival advanced nuclear thermal numbers, but the engine must survive radiation, erosion, and fierce thermal gradients over long burns. Push farther and you reach the beamed core idea. When a proton meets an antiproton, much of the energy becomes Pion's short-lived particles, many of them charged. If you trigger the reaction just ahead of a powerful magnetic nozzle, You can bend those charged pions backward so their momentum pushes the ship forward. That's a direct antimatter rocket. No intermediate propellant tank to heat, just raw reaction products turned into thrust. Paper performance looks dazzling exhaust velocity as a meaningful slice of light speed. The catch is the neutral side of the fire. Neutral pions promptly decay into hard gamma rays you cannot reflect or collimate, and they pour heat into places you don't want to cool. Add the massive shielding and radiators, and the elegance grows heavy. There is a clever middle path called antimatter catalyzed fusion. Instead of trying to burn antimatter for all your thrust, use tiny doses, micrograms or less, to ignite fission or fusion, microbursts that would otherwise be hard to start. Picture a stream of pellets, each loaded with fusion fuel, and a pinch of antiprotons injected at the right moment to spark a tidy high-gain burn. A magnetic nozzle turns each burst into a kick. In this role, the antimatter is a match, not the bonfire. You shave the antimatter requirement by orders of magnitude and lean on fusion plumbing we at least understand in principle: coils, pulse drivers, magnetic nozzles, radiators. Still hard, but closer to engineering than magic. What about the ultimate minimalist engine, the photon rocket? Matter and antimatter annihilate to light. If only we could aim that light. The physics frowns. Gamma rays don't bounce off mirrors we can build. They plow through matter, knock atoms loose, and heat everything. You could absorb them and re-radiate at lower energies, but then you're hauling city-sized radiators just to stay alive. A photon rocket is graceful on paper and cruel in hardware. Safety turns romance into procedure. A microgram spill isn't a stain you mop up. You design so the fuel never touches anything by accident. Nested magnetic bottles, quench protection that reacts in milliseconds, power supplies that fail, safe, not fail, open, and shields that survive a hit without domino failures. You route plumbing, so any loss of control dumps fuel outward, not inward. You test far from people. Antimatter's drama is exactly why operations must be boring. Could antimatter give us a 20-year trip to Alpha Centauri? On the whiteboard, yes. The specific energy is so high that a few grams, paired with a few grams of ordinary matter, could in principle fling a wafer-scale craft to a fifth of light speed and also break on arrival. In real hardware, not yet. Production rates, storage lifetime, handling reliability, and the mass of shielding and radiators say no, at least for the next chapters of our story. Even antimatter-catalyzed fusion looks like a near-term path to spectacular solar system ships and, maybe later, a slower break-and-stay mission to a nearby star, not a 20-year sprint. Are there side doors? A few. Planetary magnetospheres trap a whisper of naturally made antiprotons, born from cosmic ray collisions and corralled by magnetic fields. Concepts exist for harvesting that trickle with tuned magnetic scoops. The flux is tiny, but catalysis doesn't need much. Another door is hybrid architecture. Accelerate with Earth's laser array, then carry a microscopic antimatter package to ignite a fusion break at the destination. Now you're talking micrograms, not grams, and a capsule that stays cold and quiet for decades before one perfect shot. So where does that leave antimatter? In mission design terms, it's a wild card. As a prime mover, it demands miracles in production and containment. As a catalyst, it could become a sharp tool in a kit we're already building for fusion and pulsed propulsion. If breakthroughs arrive in lighter, higher temperature superconductors for magnetic bottles, in direct energy converters that turn charged, particle spray into clean electricity, in radiator materials that dump heat with less mass, then the slider moves from fantasy toward plan. Until then, the laser sail remains the most credible way to see Alpha Centauri up close within a single human generation, with nuclear thermal and nuclear electric engines building the logistics that make even that possible. But credible is not easy. Dust hits at relativistic speeds, pointing tolerances, deep space communications, and global governance are still cliffs to climb. And one question looms over every sprint: that refuses to carry propellant. When you arrive, how do you slow down? The answer may be to use the medium itself as your brake. Next, we'll explore propellantless deceleration magnetic sails that grip the thin interstellar plasma, electric sails that ride stellar winds, and photon tricks that use a destination star's light as a hand on the brake. Start with the blunt truth. If you refuse to carry propellant, you must borrow a brake from the environment. Space gives three invisible handles: magnetic fields, charged particles in stellar winds, and light. None is strong. At 1/5 light speed, you approach a star like a skipping stone. Time inside any handle is brief. Still, a small slowdown can stretch a flyby from seconds to minutes. A magnetic sail is a parachute made of force. Run current through a loop and you create a magnetic bubble. As you plow through interstellar plasma, that field deflects charged particles. Their change in momentum becomes drag. In the probe's frame, the plasma looks denser and faster, which helps. But you also arrive hot, so braking time is short. A mag sail needs area kilometers of loop. A gram-class wafer cannot carry that. A ton-class ship might. Engineers try to cheat size with inflation. A plasma magnet injects ionized gas into a small coil. The ejected plasma drags field lines outward, inflating a far larger bubble. Near a star, where fresh wind feeds the bubble, it can tow a small craft like a kite. Far from stars, the bubble sags, then strengthens again in Alpha Centauri's wind. A pocket plasma magnet could shave a few % of speed and stretch a flyby, not capture from 0.2 C. An electric sail swaps magnets for charge. Imagine hundreds of hair-thin tethers at tens of kilovolts positive from a tiny electron gun. Protons in a stellar wind feel the field and veer away. The deflection steals momentum from the ship. Electric sails shine inside a few astronomical units of a sun. For interstellar braking, they face two hurdles. The medium is thin and a 0.2 C. Approach leaves little time. You get a trim, not a stop. Light offers subtler leverage. Photons carry momentum. The same mirror, bright sail a beamer, used to push, can face the destination star and act as a brake. Near a star, photon pressure rises while gravity curves your path. With exquisite navigation, you can tack against light and gravity together a photogravitational assist. Around Alpha Centauri A and B, you can choreograph a figure 8 that trades velocity for course changes. It can shave tens of kilometers per second, not tens of thousands, unless a second beamer at the destination helps. You can bake extra photon control into the sail. Diffractive metasurfaces, ultra-thin patterns that steer light let the sail switch optical behavior. Earth's beamer could push in one color while the sail stays transparent to starlight during cruise. Near Alpha Centauri, a flip could make the sail reflect the local star's light strongly, squeezing a few more % of braking than a plain mirror. It is free performance, not a capture plan. There is a brutal idea called the mass shield. Put a thin, sacrificial bumper ahead of the probe. As you hit interstellar gas and dust, the bumper ablates and carries momentum away, protecting the payload and barely slowing the craft. The arithmetic is merciless. To shed a large fraction of speed, you must plow through, and thus carry, a mass of interstellar matter comparable to your own. For gram-class probes, this is hopeless. For heavier craft, it becomes a real but expensive brake. So do magnetic, electric, and photon brakes disappoint at sprint speeds? Yes. Are they useless? No. They buy margin. A tiny loop might trim a % in the last years. A diffractive sail tuned for Alpha Centauri A's spectrum might nudge the trajectory toward a target world. When your science window is minutes, small knobs are gold. Change the scale and you change the verdict. Accept a 100-year cruise at 0.030.05 C and a real mag sail, kilometers across, can engage the interstellar medium early and brake for decades. As the ship enters the destination system, an electric sail unfurls thousands of kilometers of charged tethers to ride the local wind. Photon, tacking at the end, seals the capture. That is not a postcard mission. It is a freight train. It delivers orbiters, landers, and relays. There is one brute force answer that makes all the brakes sing but moves the problem instead of solving it. Build a beamer on the far side. If a second phased array waits in Alpha Centauri, it can flood incoming sails with counter-light and decelerate them as hard as Earth accelerated them. Add photon assists and a magnetic brake to spiral into orbit. The price is building the engine twice and shepherding heavy hardware across light years. Alpha Centauri's layout helps. A and B provide strong light and helpful gravity. Proxima, dim but tempestuous, likely blows a stiff wind and hosts a tangled magnetic field. A magsail can grip that in the last stretch. A smart program staggers arrivals. First gram, scale sprinters to map hazards and taste the winds. Then slower, heavier craft with real brakes that use those maps to target safer captures. For the mission, we can launch soonest the wafer-scale sprint. The conclusion is simple. Arrive hot, accept a flyby, and design the encounter to squeeze science from minutes. Bias the hardware toward exquisite pointing, fast sensors, and a laser link that dumps data quickly. Add cheap helpers, a small magnetic loop, a diffractive brake mode, a forward shield that both protects and, in the tiniest way, drags. None turns a sprint into a stop, but all widen the hourglass a little. Later, with infrastructure, the story changes. Grow superconductors that hold stronger fields with less mass. Practice inflating plasma bubbles that act like parachutes. Build power and optics off Earth. When those pieces are routine, magnetic and electric sails become brakes you can bet a mission on. Between now and then, how do we slow down? Stays the sharpest question. The first answer is that you don't. You fly through and listen long. The second is that you borrow what the universe offers: fields, wind, and light, and you take every percent it gives. The third is that you build the missing half of your engine at the destination. None is easy. All are pathways. 3 acts: push, coast, encounter. Put almost everything controllable on Earth into the first act. That is how a 20-year sprint stays sane. Act 1 starts years before launch. The beamer grows as a modular campus in a high desert. Teams rehearse with handkerchief sails ejected from CubeSats, bathing them in tens of kilowatts to prove wavefront sensing, beam tracking, and self-centering. Nuclear electric tugs ferry spares and practice debris-clearing nudges so the array earns its keep before it ever points outward. Launch day is plain. A small rocket places a dispenser in high elliptical orbit. After checkout, the dispenser opens and releases a compact package the size of a thermos. Sail rolled, payload wafer tucked behind a forward shield. The package drifts to a corridor where geometry, weather, and beamer schedules align. Deployment is choreography. A memory metal hoop warms and snaps the film into a clean circle. Slender booms square the rim. The wafer sits centimeters behind the sail, in shadow. A tiny spin stiffens the membrane. Star trackers read the sky and hand attitude to the sail's passive stability. Electrostatic tabs on the rim trim what shape alone cannot. Acquisition is a duet. The array first sends a faint calibration beam, while adaptive optics pre-distort for turbulence. Cameras lock onto the sail's glint. When the wavefront is flat and the glint steady, power rises. The main beam floods the membrane in a narrow color. Almost all light reflects. The small absorbed fraction must be shed as heat. Acceleration jumps to thousands or tens of thousands of G and holds for minutes. The sail does not roar. It shimmers as pressure and spin keep it centered. Cutoff is scripted. As the spot swells and flux falls below useful levels, shutters close. The sail tips to dump stragglers. The wafer tucks behind its shield. and the profile turns edge-on to shrink dust cross-section. Spin resets to a slow, stabilizing roll. Act 1 ends with silence. Act 2 is 2 decades of coast. Power is rationed. Thin-film solar helps for the first few astronomical units. Beyond that, a tiny battery and energy harvesting circuits take over. The probe lives on wake windows, weekly early on, monthly in mid-cruise, yearly in the deep. Each wake brings chores, star fixes, clock discipline, memory scrubbing, health beacons, and nanonewton trims from field emission micro thrusters. The rest of the time, the craft sleeps edge-on to minimize dust hits. Navigation is stubborn and autonomous. Round-trip light time soon stretches past a decade. The wafer cross-checks bright stars and background quasars. When geometry allows, it locks faintly onto the destination pair to shave pointing error. Pulsar timing rides as a backup clock. Hazards are handled statistically. The forward shield layered polyamide, aerogel, or graphite foam soaks thousands of small hits and survives a rare larger one. A dust counter logs pings to update risk models. If counts rise above forecast, the wafer rolls a few more degrees to harden its profile. The sail's coating shrugs off ultraviolet and cosmic rays. Freckles from micrometeoroids are expected, not fatal. Act 3 starts years before arrival with rehearsals and turns urgent in the last days. Arrival is a precision drive-by. The goal is to turn minutes into a documentary. Weeks out, the probe increases wake cadence, checks gyros, and clears memory. Days out, it runs full-dress simulations while Earth listens to status beacons. Hours out, it locks attitude, toggles a diffractive brake mode if even a fraction helps, and executes a sealed command sequence. Instruments are built for speed. The camera is a MEM-steered eye with a global shutter and microsecond exposures. At 60,000 kilometers per second, 1 millisecond of smear is 60 kilometers. A micro, mirror D, scans opposite the motion to freeze scenes. The spectrometer uses thin film gratings and a line sensor tuned to key bins, water, vapor, and carbon dioxide bands, stellar, wind lines, and dust glow. A magnetometer rides on a short boom. A dust counter timestamps impacts and estimates grain size. Targeting is triage. Alpha Centauri A and B are bright and close. Proxima is dim, stormy, and possibly planet-rich. One wafer cannot see everything. The program splits the swarm. Some probes bias for the A-B pair during a geometry that favors photogravitational trim. Others aim for Proxima's corridor to sniff its wind and graze the likely orbit of the temperate world. Each wafer plays one script. Together, they cover the system. Data triage is a quiet fourth act. Bandwidth is ruthless. Immediately after closest approach, the probe pivots to communications. The sail becomes a dish or mirror, and the wafer's tiny laser begins a torrent of structured whispers. First out are thumbnails, health, and time tags. Then come gold frames, the best images and spectra pre-ranked on board. The rest trickles for months and years, using photon-efficient schemes such as pulse, position modulation with heavy error correction. Giant receivers on Earth and the Moon listen. Then there is silence for 4.37 years while light carries the message home. In that intermission, ground teams comb thumbnails, tune deconvolution, plan follow-ups for the arrivals behind, and brief a waiting public without hype. Now step back and see why the architecture front-loads effort into Act 1. When your spacecraft is smaller than a sparrow and your burn lasts minutes, you dodge a trap that haunts big missions: the need to be perfect for decades. The wafer must be robust for minutes and resilient for years. The infrastructure, the beamer, the receivers, the factories that stamp tiles and sails is where perfection belongs, because it can be serviced, upgraded, and reused between star shots. Built this way, a 20-year sprint stops sounding like magic and starts looking like logistics. You book weather, power, and sky, not miracles. You let a chorus of small craft cover for each other's bad luck, and you promise nothing fancy at the end. No orbit insertion, no grand tour, just a razor-sharp skim through another sun's breath and a packet of truth that follows at light speed. You only get to learn what you can hear. Everything else, lasers, sails, shields, 20 years of cruise means nothing if the probe cannot speak loudly enough across 4 light years, and we cannot listen quietly enough. Communications is the fourth wall of interstellar flight, a problem that turns into poetry when you realize each image is carried by a rain of single photons arriving out of the dark. Start with the brutal geometry. Brightness fades with a square of distance. 4 light years is about 40 trillion kilometers. Even a tight laser beam spreads a little, and every tiny spread multiplies at that range. A gram-scale probe cannot host a big transmitter or a heavy power source, so it must talk like a firefly short, sharp flashes timed so precisely that a receiver knows where to look in time, not just in space. That is why optical beats radio for the wafer probe. Radio waves are generous to point, but stingy with photons per square meter. Visible and near-infrared light pack far more photons into a narrower beam for the same power. The plan is photon-efficient signaling, pulse, position modulation, where information hides in the timing of faint flashes rather than in continuous brightness. You spend your scarce energy arranging a handful of photons into slots the receiver expects. Then you let error-correcting codes do the rest. The transmitter is humble but cunning. The wafer carries a chip-scale laser diode driven in bursts, disciplined by radiation-hardened oscillators, and a tiny heat spreader that bleeds waste heat into space between pulses. The sail itself becomes hardware again. During cruise, it sleeps as a shield. During downlink, it acts as a mirror dish. By bending slightly, it forms a weak optical antenna that tightens the beam without adding mass. A micro-actuated tip-tilt element steers milliradian corrections as the probe tracks the target receiver. Pointing is half the battle. Imagine trying to aim a laser at a coin on the moon while you are on a boat. The boat is your wafer, nudged by dust hits and micro-thrusters. The coin is a telescope on Earth or on the moon. The cure is choreography. Long before arrival, the probe watches bright stars and quasars to refine attitude. As the encounter ends, it snaps a final star fix, locks the sail dish, and begins a timed downlink campaign aimed at a schedule of receivers already listening. Receivers come in layers. On Earth, large optical telescopes fitted with adaptive optics and single photon detectors stare at the patch of sky where the probe should be. They do not collect a picture. They listen for clicks in carefully spaced time bins. The atmosphere dances, but wavefront sensors and deformable mirrors flatten the starlight's chaos enough that faint, narrow-band flashes rise above the twinkle. Night after night, an array of observatories hands off the baton as the Earth turns. The moon is better. No air, no weather, no twinkle. A purpose-built optical array on the lunar far side, shielded from Earth's radio and light clutter, would be the quietest ear humans can build. Mirror segments need not be supersized if there are many. Their signals add in software. Cryogenic single-photon avalanche diodes or superconducting nanowire detectors sit at the focus, counting and time-tagging photons with picosecond precision. The moon's slow day-night cycle lets radiators stay cold and detectors calm. Between Earth and Moon, you can form a virtual antenna, correlate time tags from multiple telescopes, and you suppress noise that is local but preserve flashes that line up across the network. It is the optical cousin of very long baseline interferometry, familiar to radio astronomers, repurposed for communication. Every station keeps time against a common standard. Deep clocks rule this kingdom. Hydrogen masers, optical lattice clocks, and smart algorithms that carry stability across months. There is an even stranger receiver, the Sun itself. At roughly 550 astronomical units, the Sun's gravity focuses light from a distant source into a needle-thin ring, the solar gravitational lens. A relay parked on that focal line can, in principle, harvest an enormous effective aperture. It is hard. The craft must sit hundreds of billions of kilometers away, track a moving ring as Earth and Alpha Centauri drift, and separate the desired signal from the Sun's own glare. But the gain orders of magnitude in photon collection is intoxicating. A far future architecture could fly a single Gravi ear to listen not only to the wafer, but to many interstellar craft by hopping focal lines. Back to the near term. What bit rates are honest for a gram-scale probe? Think of tens to hundreds of bits per second during the best passes to the biggest receivers, then trickles for months. That sounds tiny until you remember that the news value lives in a few frames and a few spectra gold frames ranked on board by quality. Compression does heavy lifting, wavelet schemes for images, line, list extraction for spectra, and aggressive region of interest coding, where the probe itself tags features worth the bandwidth. The first packets are thumbnails and health. Then come prioritized bursts. Everything else follows if power and geometry allow. Error correction is your parachute. Codes like LDPC or Reed-Solomon wrap each packet so a receiver can rebuild what the vacuum mangled. Interstellar scintillation variations in density along the path makes brightness flicker. The cure is interleaving, shuffling bits across time so a bad minute does not kill a whole frame. Receivers can also stack repeated transmissions, adding signal like water filling a bucket. If a frame matters enough, the probe schedules it many times over weeks. Power is rationed like a polar expedition. The transmitter wakes only when geometry is excellent. Between sessions, the wafer cools and sleeps. A tiny radio beacon kilometers wide on the ground acts as a lighthouse for acquisition so the laser link can tighten later. If the clock drifts, the probe sends a known comb pattern the receivers can use to resynchronize time bins. Security is not drama but hygiene. The probe's protocol is public. Its keys are not. Commands sent during cruise rare, delayed by years, are authenticated, so a random burst of light or a well-meaning amateur cannot flip a mode. Downlinks are signed so false positives do not fool eager analysts. In practice, autonomy rules. The sealed encounter sequence is already on board when the probe passes the point of no return. Why not just build a bigger transmitter? Mass. Every gram given to optics and power is a gram not given to shield or science. The elegant answer pushes cost to the ground. Build better ears, not louder mouths. The same lunar array that hears a wafer can serve astronomy between downlinks. It can time pulsars, watch exoplanet transits, and test quantum detectors under perfect skies. Infrastructure earns its keep when it wears many hats. There is one more trick worth naming because it feels like cheating: reflective relays. A later, heavier craft cruising at a few percent of light speed could unfurl a big passive mirror decades out and act as a way station, reflecting a probe's weak beam toward home. Mirrors do not need power. They need pointing. The geometry is messy, the timing unforgiving, but a program that launches a swarm can afford to try clever geometry at least once. In the end, the comm story echoes the entire mission philosophy. Make the probe simple, make the ground smart, and accept that a whisper, if well-timed and well-heard, can carry a universe of meaning. The first clean spectrum of Proxima's wind. The first color image that resolves the AB pair as suns, not points. The first hint of reflected blue or brown from a world we have argued about for decades. A handful of megabytes can change what we think the night sky is. That is what the network is built for, to catch a message written in photons from another sun and bring it whole to ours. Next, we turn to the postcard itself, what instruments a wafer can carry without lying to the mass budget, what they can measure in minutes, and what a best-case flyby of Alpha Centauri might actually show. What can a postage stamp spacecraft actually carry and still tell us something real in minutes? Think of the payload as a tight little band. One eye for pictures, one ear for spectra, a few feelers for dust and wind, a compass for fields, and a whisper, strong voice. Every gram must serve twice. Start with the eye. A wafer can host two cameras, a wide finder and a narrow detail camera. The wide eye grabs context, catches the target in frame, and hands guiding to the narrow eye. The narrow eye is a tiny telescope a few millimeters to a centimeter of effective aperture with a fast global shutter CMOS sensor. At about 1/5 light speed, you cover 60 kilometers in a millisecond. So, exposures must be microseconds to avoid smear. That is photon-starved. So the optics favor bright bands and a modest pixel count. Diffraction sets the best case. At visible wavelengths, a 1 centimeter aperture resolves on the order of 10 arcseconds. At 1,000,000 kilometers, that is tens of kilometers per pixel, at 10 million kilometers, it is hundreds. Coarse, but enough to separate crescent from gibbous, cloud from land, ring from halo. Next, the ear. The spectrometer is not a wheel of heavy glass. It is integrated photonics, etched waveguides, and a nanograting that spreads light across a short line sensor. You do not chase fine spectral detail, you chase honest, robust bands. In the visible and near-infrared, that means water vapor bands, the oxygen A band, carbon dioxide bands, and broad color slopes that betray clouds, hazes, or bare rock. Around Proxima, a cool red star prone to flares, you expect more near-infrared signal and violent time variation. The instrument banks on short integrations and onboard ranking. If a flare washes the frame, you flag it and move on. Fields and particles round out the feelers. A postage stamp magnetometer, AMR, or flux gate on a little boom measures local magnetic field strength and direction. A primitive plasma probe, think a biased wire, or patch samples electron density and temperature. A dust counter logs hits on a thin piezoelectric film, converting pings into sizes and rates. A radiation dosimeter watches the ambient storm. None of these need big optics. All can be printed, bonded, and tested as a unit. Navigation sensors double as science. The star tracker that keeps attitude to arcseconds also records stellar brightness, catching flares and microdips. The microgyros that hold pointing through a burst also feel dust nudges statistically. The comms laser can momentarily act as an illuminator for a glint experiment off a ring or dust sheet. On a wafer, redundancy is versatility, not spares. Power and timing are ruthless. Early in cruise, thin-film solar buys a margin. Deep in space, the payload lives on duty, cycled milliwatts and short watt, level bursts. The clock is a hardened oscillator, steered by occasional star fixes. Timestamp accuracy, microseconds, matters because image desmear and pulse, precision downlink, both live on timing. So what can you measure in minutes at Alpha Centauri? For a best-case Proxima corridor, the wafer aims to graze the orbital distance of Proxima b. If you pass within a few tens of millions of kilometers, the narrow eye can resolve the planet as a disk of several to a few dozen pixels across at peak, enough to see a bright crescent versus a dark limb, enough to detect cloud belts or a strong day-night contrast. The spectrometer grabs short stacks centered on water and carbon dioxide bands. If there is a thick atmosphere with clouds, you expect muted surface color and deep, broad water absorption. A barren rock shows strong color slopes and little vapor. Oxygen's A-band is alluring but tricky. On a dim, flare, active M-dwarf, it competes with noise and geometry, and biology is not the only path to oxygen. The dataset is a hint, not a verdict. As the probe speeds past Proxima, the magnetometer and plasma patch map the stellar wind on a sub-second cadence. If Proxima's wind is fierce, as models suggest, you should see a sharp rise in density and field strength as you cross the planet's orbit. and perhaps a blip if you pass through a wake or magnetotail. Dust hits spike near any debris bands. The counter turns that into grain, size distributions, constraining how raw and busy the system is. For Alpha Centauri A and B, the story shifts. They are sun-like, bright, and in a wide binary dance. A wafer scripted for an A-B pass does not expect a certain planet at a certain place. It expects stellar variety and a search for structure. The wide eye photographs the pair as suns, not points, against a deep field. The spectrometer samples each star's light for activity lines. The magnetometer and plasma probe taste a solar-like wind, testing how sun-like the twins really are up close. If the flight path crosses suspected belts of dust, the camera hunts for forward scattered glows and the counter for impacts. If a giant planet happens to be in the right place, good luck and swarm size decide that you may catch a crescent arc or a ring plane glint. The mission is designed to be surprised, not to force a bullseye. Onboard triage turns minutes into megabytes that matter. The wafer ranks frames by sharpness and novelty, keeps the top few percent lossless, compresses the rest with aggressive wavelets, and prunes anything blurred past use. Spectra are reduced onboard to line strengths and summary indices, with a few raw cuts preserved. The particle sweep bins counts rather than blasting every tick mark. All of it is tagged with attitude quaternions and nanosecond class timestamps so ground can reconstruct geometry later. What does best case look like in your feed years after launch? A short clip of Proxima's wind rising and falling as the probe crosses the orbital distance of Proxima b, giving the first in situ profile of a red dwarf breeze. A postage stamp image sequence of a tiny crescent disk waxing and shrinking over a few dozen seconds course, but unmistakably a world paired with a color curve that leans blue or brown depending on clouds and surface. A handful of spectra with a quiet notch where water should be, or not. For A and B, a clean two-sun portrait, field and particle traces that read like the Parker Solar Probe's cousins, and maybe a dusty glow hinting at a belt you will argue about for months. Constraints are part of the truth. You will not get postcard pretty maps. You will not read city light rumors. You will not weigh an ocean from one wafer's spectrum. But the first resolved disk of a nearby exoplanet from a human-made craft, the first taste of another star's wind at arm's length, the first direct dust counts in a system we can name. Those are firsts that change the next designs. Designing for minutes is a mindset. Instruments favor speed over ultimate sensitivity, robust bands over delicate lines, global shutters over rolling ones, and honest timing over heavy optics. The science plan favors ensemble truth over single probe heroics. Many wafers, many corridors, many angles. Put that together with a ground network that can hear a whisper, and a tiny probe becomes the sharpest scout we have ever thrown at another sun. Next, we zoom out and cost it. Tiles, power, sites, receivers, wafers, ride shares. How big is the bill? What buys down risk fastest? And which milestones tell the public we are on track long before any star comes into view? Put numbers on the dream, not to kill it, but to steer it. The smartest path to an interstellar attempt is to build infrastructure that earns money, shows progress in public, and retires risk in small bites. Each piece should be useful even if the Starshot slips. Phase 0 is ears and tiles. Start with receivers because they help astronomy on day one. Retrofit a few large Earth telescopes with single photon detectors and nanosecond time taggers. Add a tiny optical array on the lunar far side where there is no air or weather. In parallel, open tile factories that stamp laser modules emitters, phase control, power electronics, cooling into panels like solar PV. Every batch is burned in, mapped, and binned, so weak modules never reach the field. Phase 1 is proof by pushing. Fly orbital sail demos big enough to measure and cheap enough to lose. A CubeSat unfurls a handkerchief sail. A ground array paints it for seconds. Cameras record wavefront lock, self-centering, and acceleration. Repeat from multiple sites and in rougher seeing until success looks boring. Between shots, sell a debris-clearing service. Low-power nudges that hasten the re-entry of dead satellites, with safety interlocks and sky corridors rehearsed for the big array. Phase 2 is adolescence. Scale the beamer from practice field to campus. Modular tiles push the aperture toward a square kilometer. Add serious energy storage, so the campus charges slowly and discharges in minutes. Run high-power shots on subscale sails in very high Earth orbits to stretch beam time. Grow the lunar array to dozens of mirrors and practice coherent time-tag listening as a network. Phase 3 is the first sprint. Do not bet the farm on a single wafer. Fly a cadence. One probe per clear week for a season, each with a slightly different sail or script. The array charges for days and fires for minutes. Publish a live scoreboard, launch dates, measured accelerations, and health beacons. Anyone can plot. Price it in buckets, not one scary line. Buckets include tile factories and supply chains, the beamer campus and its grid tie, energy storage, adaptive optics and phasing metrology, the lunar array with power and cooling, the wafer line for sales and payloads, rideshare launches, and the software that keeps clocks, pointing, and safety honest. Spending is staged because each bucket is modular. If one vendor slips, another fills the gap. If storage lags, early shots are shorter but still valuable. Risk retires in layers. Materials risk falls as sail films survive hotter beams in vacuum chambers, then in orbit. Controls risk falls as ground arrays hold lock on shakier days. Operations risk falls as debris nudges and cislunar cargo tugs become routine. Communications risk falls as the ears catch fainter pings from farther test craft. Regulation and safety are design constraints, not footnotes. A high-power beam lives inside a locked sky corridor. Automated maps and radar watch for aircraft, birds, and satellites. Shutters close in milliseconds if anything strays. The site posts daily advisories and post-shot logs. Environmental reviews track waste heat, land use, night sky brightness, and wildlife. Energy is a program inside the program. The beamer's appetite is pulsed, so storage is king. The campus should soak up surplus when wind and solar overproduce, then fire on calm, clear nights. If the site sits near pumped hydro or salt caverns, it can buy cheap electrons and sell grid stability in return. On the moon, long nights ease cooling but stress power continuity. Nuclear, electric tugs, and small surface reactors already useful for cislunar logistics can anchor that grid. People and cultures set cadence. This is a spaceport crossed with a semiconductor fab. Tile lines improve on 6-month cycles. Sail films iterate like smartphone cameras. Flight ops runs like commercial space. Numbered shots, documented holds, boring checklists. If a tile lot is bad, you scrap it without drama. If a sail tears, you fix the recipe, not the story. Show the world progress while waiting years for a postcard. Maintain a debris-clearing dashboard that lists defunct objects nudged into safe decay. Post a monthly faintest signal record from the lunar array. Ship student kits so classrooms can detect calibration flashes and contribute real data. Release short explainers that stitch together lab footage, beam tunnel tests, and orbital demos. Do not hype what you cannot yet do. Televise what you just did. Where do you cut if money tightens? Protect the ears and the wafer line. Without hearing and without probes, the rest is a museum. Scale the beamer more slowly, accepting lower top speeds in the first season. Launch one probe per month, not per week. Lean on public, international, and commercial partners, telescopes, utilities, lunar operators, to keep cadence steady. The plan survives because it is modular and useful at every size. Make one last accounting that does not fit in a spreadsheet. Done right, this program improves near-Earth space, fewer debris risks, better tracking, and cleaner ways to move cargo with photons instead of propellant. It grows a generation that treats transparency as a requirement and safety as a reflex. It builds instruments that deepen astronomy the night after each test. The bill is large, the dividend is larger, and it starts paying now, not in 26 years. Next, we return to sharp edges, pointing budgets, and dust. How to compute what a single bad microradian costs you 2 decades later, and how to turn statistics on interstellar grit into a shield you can actually pack. Pointing and dust are the 2 quiet killers of a 20-year sprint. They do not explode, they accumulate. A tenth of a microradian today becomes millions of kilometers 2 decades from now. A speck you would ignore at walking speed becomes a blowtorch at 1/5 light speed. Start with geometry. 1 light year is about 9.46 trillion kilometers. Alpha Centauri is 4.37 light years away, so the range is 4.1 Chamden 10 UQGs. Missed distance equals angular error times range. A 1 microradian aim error multiplied by that distance is 4. 1 chimtenst km of miss. If your science corridor is 10 million kilometers wide, the combined system must live near 0.25 microradian. That tiny number sets design culture for optics, sales, and guidance. Turn it into a budget. Give the beamer plus atmosphere 0.1 murad with adaptive optics and phasing locked to the sail's glint. Give the sails 0.08 murad via a profile that self-centers under pressure and a slow spin that damps ripple modes. Give star tracker attitude and microthruster trim 0.05 murad, old 0.02 murad in reserve. A single arc-second measurement is 5 murad. Statistics rescue you many stars, many frames, filters that squeeze noise over time. Timing hides inside pointing. At 0 kilometers, 1 millisecond of schedule slip equals 60 kilometers, a long track. 10 milliseconds moves a closest approach snapshot by 600 kilometers. That is fine inside a fat corridor, but it is why the wafer treats time as a science signal. Pulsar cross checks, star field fits, and disciplined oscillators keep exposures where the target really is. Now for dust. The interstellar medium is thin, not empty. At 0.2 C, tiny masses carry brutal energy. A 1-micron silicate grain, 10 manusans, quarter kilogram, hits with tens of joules. A 10-micron grain is 1,000 times more massive and lands with tens of kilojoules. A 100-micron outlier climbs into megajoules. Big grains are rare, but the path is long. Statistics, not armor, decide survival. You cannot tank armor a gram, so you play odds and angles. Fly edge on after the push to slash presented area. Put a layered Whipple-style shield forward, low. Z materials like polyamide, aerogel, or graphite foam, spaced so the first layer vaporizes a grain and the second absorbs the plume. Survival is not no damage. It is no through hole. Add a faint vapor, pre-shield a slow bleed from a tiny cartridge that ionizes and spreads incoming hits a few centimeters ahead of the bumper. How many hits do you expect? Use n minus n tepel a tepels l. If troublesome micron grains average a few centon minus 22 per many q, a cross-section near 0.01, 0.03 m quadrad, and a path 4 centon 00 bash m, n is order unity at that size for the whole trip. Make a 10 times smaller by flying narrow, and you divide n by 10. Split the mission into a swarm, and the risk per postcard falls again. This Poisson logic is why many small beats one big for sprints. Populations vary. The heliopause filters grains by size and charge. Alpha Centauri's winds will do the same on arrival. Early in the mission, solar radiation and fields can charge and deflect some grains. Deep in the dark, you meet the raw interstellar mix. The shield assumes the worst, while the probe also measures the medium as it goes. Orientation is part of shielding. Keep optics in the sail's shadow, use slow spin to share freckles, and accept cosmetic damage on the sail after the push. It can still serve later as a shallow dish for the return laser. Electronics face radiation and single-event upsets. Survive with rad-tolerant parts where mass allows, triple modular redundancy on critical logic, error-correcting memory, and non-stop scrubbing, periodically rewriting correct data over flipped bits. A dosimeter acts like a metronome. When dose rates spike, shorten wake intervals to clean memory and verify state. Dust can masquerade as pointing noise. A micro-hit kicks the wafer, looks like a gyro bias, and tries to smear your frame. Cure it with diversity. Star, tracker residuals, gyro rates, and magnetometer readings feed a filter that flags an impulsive hit within milliseconds. If a kick lands during an exposure, a micromirror to scan can still freeze the scene by slewing opposite the motion for the microseconds that matter. Tie small effects back to heat. Pitting roughens surfaces and raises absorptivity by fractions of a percent. That warms the wafer during sunlit cruise and elevates sensor noise. Counter with high emissivity backs, tiny heat spreaders under detectors, and duty cycling that schedules cold windows before critical imaging. For a close pass, bias the timeline so the wafer is coldest at the top of the run. Finally, formalize randomness. Before launch, publish a hazard model. Expected dust counts by size, shield life by fluence, angle, error growth. If a star tracker loses guide stars during cruise, log pings from the dust counter and dribble those home with housekeeping. So later, wafers update aim corridors and shield recipes. If a probe dies, where and when matters as much as why. That timing and location retire risk for the rest. Pointing and dust do not make headlines, but they decide whether a postcard exists. The cure is not heroics. It is budgets and boring habits. Share the angle rent among optics, sail, and guidance. Keep the clock honest. Trim cross-section, layer a smart shield, and let a faint vapor veil take the worst edges off hits. Fly many, expect losses, and measure the medium as you go. That is how unforgiving math becomes manageable risk. Next, we fold these budgets into encounter design, choosing corridors through Alpha Centauri that maximize science per milliradian, dividing a swarm across A, B, and Proxima, and turning seconds of data into a story people can follow. Design the encounter like a stage play with marks on the floor. Each mark is a science corridor, a skinny tube of space that trades risk and reward for a specific payoff. The corridor is defined by three things: closest, approach distance, approach angle, and timing. Your pointing budget says how tight that tube is. Your dust model says how bold you can be. Your instruments decide whether the payoff is worth it. Split the system into three theaters. The AB theater is bright and forgiving. Alpha Centauri A and B are sun-like and widely separated on human timescales. Here the goal is not a bullseye on a known planet, but a clean, fast taste of two familiar stars and their environment. Corridors run a few to a few tens of stellar radii from each photosphere, close enough to feel the wind and see coronal structure in scattered light, far enough to avoid cooking a wafer or saturating sensors. Approach from slightly above the system's plane, so the wide camera can hold both stars in frame across seconds. Then pivot to sample each wind in turn. A forward scatter geometry, sun behind the wafer, dust ahead makes any circumstellar dust glow brighter. Schedule those passes when binary separation gives you a safe lane between the stars. The Proxima theater is sharp and dangerous. The star is small, flares hard, and its likely planet Proxima b orbits tight. You do not chase a postcard of continents. You chase proof of environment. Corridors form a fence that cuts across the expected orbital annulus at multiple longitudes and inclinations. Each fence slat is timed to graze the planet's orbital distance with a slightly different tilt and phase. If the planet's exact plane or longitude is off by a few degrees, some probes still cross the wake or magnetotail. Flares add timing chaos, so scripts keep exposures short and dynamic range high, ranking frames on the fly and discarding ones washed out by sudden light. Now layer in trim you can actually afford. Photon tacking is free delta V if you plan for it. A diffractive sail mode that reflects Proxima's red light more strongly than sunlight lets a probe bias a hair toward or away from the star in the last months, near A or B. A mirror-bright mode does the same. The gains are tiny meters per second at best, but over months they slide a flyby by thousands of kilometers, sometimes enough to shift from empty space into a dust-bright corridor. Build scripts like decision trees, then freeze them into sealed autonomy. The wafer can branch on a few honest signals. Star, tracker residuals, you are off-center. Radiometer spikes, a flare. Dust counter rates, you are crossing a belt. And magnetometer swings, you hit a wind boundary. If a flare blooms, the camera drops exposure and the spectrometer shifts bands. If dust rates jump, the wafer slews a few degrees more edge-on and favors protective cadence. If the magnetometer snaps, the plasma probe increases its sampling rate for a short burst. Each branch has a budgeted time and power window. After the burst, the main script resumes. Divide the swarm with intent. Allocate, say, 40% of wafers to the AB theater, 40% to the Proxima fence, and 20% to wildcards that aim at dust belts, Trojan-like longitudes, or geometry that maximizes forward scatter even if planetary payoff is low. Stagger arrivals by weeks or months, so lessons from early downlinks, dust rates, wind strength, flare frequency can refine late scripts. You cannot retarget a wafer by much once it is en route, but you can pick which branches it favors and which bins of time it dedicates to each instrument. Use stereo and statistics where resolution fails. Two wafers crossing similar lanes days apart can yield 3D with parallax at the tens of thousands of kilometers scale. Correlate their magnetometer traces to infer field topology. Cross-check dust size distributions. If one reports bigger grains, your hazard model for later arrivals updates. Even without a single hero image, an ensemble of coarse frames and fields can map belts, winds, and flare behavior. Clock the play so the audience can follow. Design encounter timelines in human units. A minute of approach, a 30-second skim, a minute of egress, each with a named goal. Publish these names before launch and use them in the eventual edit. The ground network mirrors that cadence. Earth telescopes in the lunar array schedule their deepest listening during the skim minute, then looser, longer windows during approach and egress. The first packets to arrive months later carry thumbnails labeled with those beats. Approach 3, skim 11, egress 2. Viewers will not see raw picoseconds. They will see a story with chapters. Shape the geometry to be kind to your optics. Approach angles that keep targets near the detector's sweet spot. Beat angles that force edge-of-field images. Plan slews that match the micromirror's fastest axis. Favor crescent phases for planets if you get one. A bright limb plus forward scatter may outrun color accuracy for a wafer-scale sensor. For A and B, schedule spectra when saturation risk is lowest. For Proxima, stagger short exposures around predicted flare windows. Then be ready to be wrong. Respect thermal truth. Bake the wafer cold before the run by duty cycling instruments. Then spend that cold capital during the minute that matters. If your dust model says the belt is hottest midplane, choose a slight incline that trades hits for fewer fluorescing specks on the lens. If a corridor would run closer than your dosimeter's comfort, shift to the next best corridor rather than betting the whole season on one dramatic pass. Design the downlink like the fourth instrument. After the skim, the wafer pivots immediately to point its sail dish at the best ear on the schedule. It sends a heartbeat thumbnail first, so ground nose pointing is good. Then it streams the gold frames from the skim block. Then approach, then egress, then the top spectra. If power allows, it repeats the top 10% the next night so receivers can stack 2 copies. Above all, pick corridors that each answer one simple question. How strong is Proxima's wind at the orbit of B? Is there a dust belt near A at 1.3 AU? Do A and B's winds differ at the same scale distance? Is forward scatter in this lane high enough to argue for unseen small bodies? When seconds are all you have, one clean answer beats 5 half answers. Do this and a flyby becomes a survey. Not a map, not a landing yet, but a lattice of truths strung across another sun's space. The precision your budgets bought in pointing, timing, and dust survival shows up as frames that are sharp enough, spectra that are honest enough, and field traces that are long enough to trust. Next, we put names on milestones and gates, what you must demonstrate on Earth and in orbit before anyone greenlights a full sprint, how to abort safely when a test goes sideways, and how to tell the public you are on track with numbers, not adjectives. Milestones and gates turn ambition into a checklist. They tell you what must be true before you light the big beam, what numbers unlock the next phase, and how to pause without drama if a test misbehaves. Think of them as the spine of the whole interstellar program. Short, clear sentences that decide whether the next sentence gets written. Begin with materials, because the sail is the first honest gate. Gate known as thermal honesty in vacuum. A candidate film survives megawatt per square meter. Class flux at the beamer's color without blistering for minutes, with measured absorption below a fraction of a percent and mid-infrared emissivity high enough to dump the heat. Gate M2 is passive stability. In a beam tunnel, the coin-sized sail recenters after a deliberate nudge, with damping time under a second and no runaway ripple mode. Gate M3 is shock tolerance. Coupons spun, yanked, and pulsed to the equivalent of 10,000 grams. Do not tear, wrinkle, or delaminate. If any M-gate fails twice, recipes change. The roadmap waits. Next are optics and phasing, the beamer's heartbeat. Gate bone is coherent addition at scale. Thousands of tiles lock phase on a far target for minutes with less than a 10th microradian wander after the atmosphere is corrected. Gate B2 is adaptive optics in bad air. The array holds a tight main lobe on a dim guide source through real turbulence, not lab air, with millisecond updates. Gate B3 is safety reflex. Shutters close within milliseconds when radar, LiDAR, or sky maps report a corridor incursion. Logs prove it. If any B-gate stutters, the array flies only low-power rehearsals until it's boring. Receivers are the ears. Without them, the postcard never arrives. Gate Roan is Earth-based detection. Large telescopes with single-photon detectors recover faint calibration flashes at interplanetary distances with the planned error, correcting code. Gate R2 is lunar coherence. A small far-side optical array correlates time tags across multiple mirrors and cleanly hears a deep space test source. Gate R3 is network discipline. Earth and Moon hold clocks sync over months with picosecond, class stability, and publish joint detections that outside observers can replicate. Now fly something you can lose. Gate UN is orbital push. A CubeSat unfurls a handkerchief. Sized sail, a ground array, paints it for seconds to minutes, and measured acceleration matches within 10% of prediction. Gate O2 is self-centering truth. High-speed footage shows the sail rides centered without control inputs after a deliberate offset. Gate O3 is safe disposal. After the push, the demo deorbits cleanly or moves to a parking orbit without adding to debris. If UN or O2 misses twice, materials and control loops go back to the bench before any power increase. Communications deserves its own ladder. Gate Cone is photon-efficient downlink in the wild. A deep space probe, nothing exotic, just a small craft, sends pulse. Position signals that the network decodes end to end with the real stack. Gate C2 is sail dish geometry. A subscale membrane acts as a weak optical antenna in orbit and tightens a laser beam measurably. Gate C3 is dark sky operations. The lunar array runs a week-long campaign that produces a public faintest signal record and a data release others can analyze. Shielding stands between theory and a crater. Gate's zone is hypervelocity coupon testing. Layered low, Z bumpers survive thousands of shots from a dust accelerator at energies matching the expected micron grain spectrum. Gate stew is plume truth. Instruments confirm that the first layer vaporizes the grain and the second soaks the plume without spall that would threaten a wafer. Gates 3 is vapor veil. A tiny gas bleed ahead of the shield measurably reduces crater size in the same rig. If S gates don't pass, you do not fly a fragile payload through the dark. Operations convert numbers into habits. Gate pone is no drama countdowns. The beamer runs a dozen low-power rehearsals with full sky, safety protocols, and no unplanned holds. Gate P2 is cross-team cadence. Tile lines, sail labs, receivers, and range safety hit a 2-month drumbeat without heroics. Gate P3 is telemetry hygiene. Every high-power test publishes a post. Shot report pointing, power, weather, shutters, locks, so the public can audit performance. Abort rules are part of the gates, not afterthoughts. Abort alone is beam out on glint loss. If the guide sparkle drops below threshold for more than a heartbeat, power falls to 0 and stays there until reacquisition is proven. Aborta 2 is sail flare out. A triggered rim actuator or diffractive mode deliberately decenters the sail to shed the beam if onboard sensors see overheating. Abort A3 is sky incursion. A civil aviation or space tracking alert forces a scrub without debate. The only failure here is a failure to abort. Program gates chain these pieces together. Program gate PG Alpha is green for adolescence. Moan, M3, Bone, B2, Roan, Un, and Son must all be true before pushing harder than kilowatts on anything in orbit. Program gate PG Beta is green for campus. B3, R2, O2, Cone, and Pone. 2 must be true before assembling a square kilometer, class beamer, and scheduling minutes, long shots. Program gate PG Gamma is green for season. A3, K2, STU, S3, and P3 must be true before the first sprint season. Dozens of wafers over months gets a date. Miss a PG gate and you hold, fix, and rerun. The hold itself is a success metric because it proves the culture listens to the numbers. Money and time sit inside the gates, not above them. Each gate has a cost range and a slip budget published in advance. If M2 slips by a quarter, the season's cadence shrinks by a quarter. Nothing else slides silently. If bone costs 10% more, tiles slow elsewhere, not safety. This makes trade-offs visible. Fewer wafers, not riskier wafers. Public truth keeps the coalition intact. Every gate result, pass, fail, partial lands in a monthly bulletin with plots, not adjectives. A public burn-down chart shows how many gates remain to PG Gamma. An educational dashboard lets anyone replay a rehearsal, step through a wavefront lock, or see a dust crater before and after the vapor veil. Trust is oxygen. You manufacture it on purpose. When a test goes wrong and one with a playbook is short, stop, safe, log, publish. Run a quick look within 24 hours, a root cause within 30 days, and a fix verified rerun before resuming the ladder. No villains, no spin, just engineering. By the time PG Gamma turns green, no single piece will feel heroic. The sail will be a product with a part number. The beamer will be a utility with maintenance windows. The receivers will be observatories that also do science at dawn. That is the point. You do not want a miracle, you want a machine. Set like this, milestones and gates do more than police risk. They pace a story the public can follow, give investors and agencies numbers they can defend, and create a culture that runs on evidence. When the first wafer leaves in a column of light, it will feel less like a stunt and more like a scheduled departure, because in the deepest sense, that's exactly what it is. This is where the story narrows to a point. We have a way to push, a plan to coast, and a way to be heard when we arrive, not magic machinery. A beamer on Earth that turns electricity into momentum. A wafer sail that trades propellant for photons. Receivers that catch single photons and turn them into pictures from another sun. Build the pieces in the right order, and the first postcard from Alpha Centauri becomes a scheduled message. The near term is humble and powerful. Nuclear thermal and nuclear electric ships move mass, raise stations, and stitch a logistics web around Earth and the Moon. That web pays the bills and teaches the habits, clock discipline, autonomous ops, heat rejection that a Graham-class probe will need in the dark. The beamer grows by tiles, not vows. The ears grow by mirrors, not hype. Each rehearsal does real work. Push a CubeSat sail, clear debris, prove the link from the lunar night. The sprint is simple to say, hard to do. Minutes of push, decades of quiet, minutes of encounter, years of downlink. Budgets microradians of aim, microseconds of exposure, milliwatts of power turn heroics into checklists. The swarm is our net. Many arrows along slightly different lanes make failure a statistic, not a verdict. If fusion matures, the story widens. A pocket star turns flybys into arrivals. If antimatter becomes a reliable match, it lights cleaner fusion burns. If magnetic or electric sails prove their worth, they become brakes instead of footnotes. None of those ifs must come true before the first sprint. The light sail architecture is the test we can afford and learn from now. What do we get for the work? Firsts that matter. The first resolved disk of a nearby exoplanet. The first in situ taste of a red dwarf wind. The first direct dust counts in a named system and a network that doubles as an observatory the rest of the month. There is a deeper prize. Building an engine that reaches another sun without carrying its own fuel changes how we act at home. It rewards openness, public corridors, and shared sky maps. It rewards patience. The best shot takes years to stage. It rewards humility. The probe is small. The risks are real. Stand outside on a clear night and find Alpha Centauri, 2 points to the eye, a third dim ember beside them. Imagine a wafer already on the way, edge on and silent. Imagine the beamer cooling after another rehearsal. Imagine the moon listening. One day, 26 years after a quiet countdown, a thumbnail will land on your screen. It will not be perfect, it will be enough. A small, bright curve, a spectrum with a water notch, a trace of wind rising and falling around a world we have only guessed at. That is the closing beat of this story and the opening beat of the next. We stop calling Alpha Centauri the nearest star and start calling it the nearest place. We learn with photons, not flags. We send the first hello across the long dark and wait, knowing the hardest part, choosing to begin, is behind us.